Using the one-step approach, we can model both composites using fixed weights and freely estimated weights. Here you can see the model of the one-step approach where free weights are used. That is, product intelligence is modeled as the weighted sum of its 6 components. To achieve that, we technically model product intelligence as a latent variable that is affected by its 6 components. To ensure that product intelligence is fully made up of its components, we need to fix the variance of the resulting error delta to 0. Moreover, we need to determine the scale of product intelligence. For that purpose, we fix one of the weights to 1, in our case the weight of autonomy. Further, we need to allow for the covariances between the components. In this way, we ensure that no constraints are imposed on the covariances between the components. Finally, we specify the effects and covariances between the remaining parameters of our model. If we want to use unit weights in the one-step approach, we must further constrain the weights, meaning the weights of the other 5 components. As you can see here, we fixed all the weights to 1. As a consequence, product intelligence will be the sum of its 6 components. The rest of the model specification is the same as in the case of free weights. To estimate this model, I've created a folder which contains 2 files. The data file reisdijk 2007 cov.dat, which I've already talked about in the session about the two-step approach, so therefore I won't talk about it here. And the second file is one-step unitweights.imp, which is the Mplus syntax file. So let's have a look at the Mplus syntax file. So the Mplus syntax file consists of various sections. In the first section, title, we can give the analysis a name. So here I called it one-step approach using unit weights. In the second section, data, we need to tell Mplus where our data file is located. And since in my case the data file and the Mplus syntax file are both in the same folder, it's sufficient to just mention here the file name. Then we need to let Mplus know which type of data we're using for the model estimation. Since we are working here with the variance-covariance matrix, we set type to covariance. And finally, we tell Mplus that 313 observations were used for the estimation of that variance-covariance matrix. In the next section, variable, we need to give Mplus the information about the variable names of the variance-covariance matrix, because the data file doesn't contain any variable names. So here under names, we let Mplus know that the first element of the variance or that the first variable in the variance-covariance matrix is autonomy, abbreviated with AU. The second variable is ability to learn, abbreviated as AL, and so on. And the last variable is PI score, which was the sum of its 6 components. Since we won't use PI score in the one-step approach, we need to use the use variables command to make sure that only the 10 original variables are used in the actual analysis. So therefore, only the first 10 variables are mentioned, while PI score is excluded. In the next section, here model, we come to the actual model specification. And in the one-step approach, the composite is modeled as a latent variable that is affected by its components, and therefore we need to create a so-called phantom latent variable. We can do that in Mplus by using the by command. So the by command creates a latent variable, in our case pi, which is measured by AU. But since actually pi has no measures, we fix the factor loadings to 0 using the add command. So as a consequence, we have a latent variable pi. Then in the next step, we need to specify the weights of the components to form product intelligence. So therefore, we say product intelligence is affected by autonomy. And since we want that product intelligence is the sum of its components, we need to fix the path coefficient to 1. And again, we can do that by using the add command and then type the value after it. So in our case, the path coefficient of AU on PI is fixed to 1. And we do the same for the other 5 components. Then since we want that the composite, or in our case product intelligence, is fully made up by its components, we need to fix the error terms variance of product intelligence to 0, and we can do that again using the add command. So if we type variable name, add, and then the value, we fix the variance, in that case the variance of the error term, to the value that we specified here, so in our case to 0. Further, we need to specify the covariances between the 6 components. So here we specify the covariances between autonomy and ability to learn, reactivity, and so on, and personality. In Mplus, this is done with the help of the with command, and we can do that for the other components as well. In the next section, we specify the effects of product intelligence on the mediators, so in our case on relative advantage, compatibility, and complexity, and we do that using the on command. Then we also need to specify the effects of relative advantage, compatibility, and complexity on consumer satisfaction, which is done here. So we write CS, which is the dependent variable, so consumer satisfaction, which is regressed on relative advantage, compatibility, and complexity. And finally, we specify again the covariances between the disturbance terms of relative advantage and compatibility, and the covariance between relative advantage and complexity, actually between the disturbance terms, and we do the similar thing for compatibility and complexity. Then in the last section, output, we need to let Mplus know which output we are interested in, and here I write standardized. So as a consequence, in addition to the unstandardized results, I will also get the standardized parameter estimates. So now we can click on the Run button, and as a consequence, we will get the output file. So the output file contains all the information about our model estimation. And here we can see when the analysis was carried out and which Mplus version was used. So in my case, version 8.8. Moreover, we see again the specified model or the model syntax, which I will not discuss again because I did that already. Then Mplus warns me that some of my input lines were too long, so they exceeded 90 characters. But if we have a closer look, we can see that this only refers to my comments, and therefore we can ignore these warning messages. However, if such a warning would refer to the model syntax, then you should take it serious and, for instance, introduce a line break to ensure that the model syntax is read in properly. Then we can also see the summary of the analysis here. So we have one group, which makes sense because we have not specified any group variable. Then we see again the 313 observations that were used for the estimation. Then Mplus tells us that there were 5 dependent variables in the model, which is a bit surprising because we would expect only 4. But if we have a closer look here, we can see that AU is also mentioned here, and this is because we used AU to specify the pseudo-latent variable. Similar, if we look at the number of observed independent variables, Mplus tells us that there are 5, namely these 5. Although we would expect that there are 6, namely autonomy is missing, but again, since we used autonomy to specify the pseudo latent variable, it is not listed here. And finally, we have one continuous latent variable, namely pi, but since we fixed its error terms variance to 0, pi is actually not a latent variable, but the sum of its components. Then in the next part here, Mplus shows us which estimator was used. Since we have not specified any estimator in the syntax file, maximum likelihood estimator is used as the default. And then we get here some additional information about the solver. So maximum number of iterations was set to 1000. And then here we can see that the model estimation terminated normally. So for instance, if the solver has not converged, then this would be mentioned here. In our case, an optimum was found. Further, we get some model fit information. And we see that our model consists of 34 parameters, namely the 21 covariances between the components, the 6 direct effects between product intelligence, relative advantage, compatibility, complexity, and consumer satisfaction, the 3 covariances between the disturbance terms of relative advantage, compatibility, and complexity, and the 4 variances of the disturbance terms. Moreover, we get the value of the log likelihood function for our estimated model. Then we get some information about the information criteria, particularly the AIC, the BIC, and the sample size adjusted BIC, which can be used to compare our model with other models. For instance, a model where the weights are freely estimated. Then we get also the result of the chi-square test for exact model fit. So we see the test statistic takes a value of 46.035 and we have 21 degrees of freedom, which are the number of non-redundant elements in the variance-covariance matrix minus the freely estimated model parameters. And considering the p-value, the null hypothesis about exact model fit is slightly rejected, at least if we assume a significance level of 1%. Then we have here a measure of approximate fit, the root mean square error approximation, RMSEA, and we get an estimate of 0.062, which, following established thresholds from the literature, indicate an acceptable model fit. Moreover, we get the results for the test that the population arm SEA is smaller than 0.05, and if we look at the p-value, we see this H0 is not rejected, further indicating that our model fits the data approximately well. Then we get the results for the CFI and the TLI. For the CFI, we have a value of 0.937, and for the TLI, we get a value of 0.896. Both values are a little bit lower than the proposed threshold in the literature. Still, I would say that our model fits the data acceptably well. Then we get also the results of the chi-square test for the independence model. So this is the model where all our variables are uncorrelated, and we see that this model fits the data very poorly. And as a last fit measure, we have the SRMR, the standardized root mean square residual, with a value of 0.04, which, comparing it to established thresholds from the literature, indicates a good model fit. So we can conclude that even though we take in the one-step approach the components of product intelligence and their weights into account, the model fit is acceptable, and thus product intelligence appropriately captures the collective effects of its components on its consequences. In the next part, model results, we can find the actual parameter estimates. So here we can see the loading of autonomy on product intelligence, which we fix to 0. And similarly here we can find the weights of the components. So we fix them all to 1 because we wanted that product intelligence is just the sum of its components. As a consequence, no standard errors are reported, or they are all equal to 0. And no inference can be made because the parameters are fixed. Further, in this section, we find the effects of product intelligence on relative advantage, compatibility, and complexity. They are all positive and statistically significant if we look at their p-values. And in addition, they are identical to the results that we obtained from the two-step approach using unit weights that I discussed in the other session. The same is true for the effects of relative advantage, compatibility, and complexity on consumer satisfaction. So they are also identical to those of the two-step approach discussed in the other session. And in particular, we see that relative advantage and compatibility show a positive significant effect, while complexity, even though it shows a negative path coefficient, its effect is not statistically significant, at least if we assume a 5% significance level. Furthermore, we find here the various covariances between the components, and in that part here we see the covariances between the disturbance terms of relative advantage, compatibility, and complexity. Then in this section here, variances, we can find the variances of our variables. So here we see the variances of 5 components, so ability to learn and so on, which is surprising because we would expect that also the variance of autonomy is listed here, but since autonomy was used as a measure to create the phantom latent variable, its variance is listed under the residual variances. And here we can also see the variances of the disturbance terms of relative advantage, compatibility, complexity, and consumer satisfaction. And we also see the fixed variance of the disturbance term of product intelligence. Since we asked Mplus to also report the standardized results, we can find them here in the section Standardized Model Results, and particularly we consider this STD-YX standardization, meaning that both the dependent and the independent variables are standardized. So here we can see the standardized weights. Moreover, we can find here the standardized effects of product intelligence on its three consequences, and they are identical to those from the two-step approach using unit weights that I discussed in the other session. Similarly, here we have the effects of relative advantage, compatibility, and complexity on consumer satisfaction, and they are again identical to the standardized results for the two-step approach. Then we have here the correlations between the components, and then we can continue with the last part of the results, namely the R-square table. So here we can see the R-square values for our dependent variables. So the one for autonomy is not really interesting because an R-square value of 0 is shown, since we used autonomy to create the phantom variable, and with a fixed factor loading of 0, therefore no variance in autonomy is explained. For the other four dependent variables, we can see that we get the exact same values as for the two-step approach, and then we have also a latent variable, which is product intelligence, which is actually not a latent variable because it's the sum of its components, and this is also confirmed by the R-square value because it takes a value of 1, meaning that product intelligence is fully explained by its components.